Hello and welcome to this follow-up clip for Synoptic Homework One. I'm assuming at this point that you've tried it under test conditions at home and gone back and boot camped and revised the things that you needed to get some help with. If you had to look something up, for example, you need to have paused and revised your notes, summarised them, learnt your flashcards, look, cover, write, check, repeat, etc. The kind of techniques that your teacher's been talking to you about for effective revision. That's active revision, not passive revision. Okay, so assuming you've all done that and you've got your test ready, it's in front of you right now and you're ready to go through some of the answers. This clip will take you through all the questions. We'll focus on areas where recall was required. We'll focus on how to read the question, and you may want to annotate your script as you go with some improvements. So the first one says, which pair of molecules are affected by Markovnikov's rule during electrophilic addition with HBr? So the recall required for this question is that the alkene has to be asymmetric in its structure. In other words, the C-C double bond needs to be towards one side of the structure for Markovnikov's rule to apply. So now what you've got to do is to visualize each of them. So it's quite straightforward. You start by eliminating the ones that are obvious wrong answers. So if we look at the last one, hexane and cyclohexane, it's not going to be those because they are alkanes, not alkenes. So looking at the remaining candidates. So ethene is symmetrical, so it can't be ethene and propene, so A is not an answer. So what we've done is we've tried to eliminate the two wrong answers. This is a piece of exam technique you can use when doing multiple choice questions. So this leaves 2-methylbuteene and 2-methylbuteene and 3-methylhexaonine. So let's look at the pair in part B. What I'm going to do is draw out the skeletal formulae for you, and you can decide from there. So looking at 2-methylbuteene on the left and hex3ene on the right, one of them does come under Markovnikov's rule because it's asymmetric, and the other one doesn't. So that must mean that answer B is also incorrect. So that would mean the correct answer is C. We didn't have to draw those out because we managed to eliminate all the wrong answers. So the next one is, which is an example of a tertiary alcohol? Again, there's a bit of recall required. And that is the structures of the three different classifications of alcohols. If you have that recall, then this question is easy. All you've got to do is apply it to the structures. So, hexan-1-ol is obviously not a right answer because that has the alcohol at one end. So therefore it's going to be primary alcohol. 2-methylpentan-3-ol is not correct because that's a secondary alcohol because it's got the alcohol group in the middle of the carbon chain, but the methyl group is not on the same carbon. If it was 2-methylpentan-2-ol, then yes, it would be tertiary. So 2-methylpentan-3-ol, let's just draw that out to illustrate what I'm saying. So you can see that 2-methylpentan-3-ol is going to be a secondary alcohol, so that one also is going to be incorrect. So that brings us to CH3CHOHCH3, which is part B. I'll have to draw that one out as well. And you can see that that one is also a secondary alcohol, so it's not going to be that answer. And I can just about squeeze in the structure for CH3,3COH on the left hand side, which tells us why A is the right answer. So if we go and have a look at our structures for primary, secondary and tertiary, you can see that the tertiary structure is followed by the structure in answer A. You have 3 R groups or 3 alkyl groups. Okay, so let's bring the page down a bit and do the next part. So the next part says, which is or are suitable reagents for the oxidation of a tertiary alcohol? I might be thinking, oh, fantastic, A has dichromate and it has the acidifying reagent as well. It's got Cr2O72- and H+. The key thing here is the tertiary alcohol. And there's a bit of recall required here. In the tertiary alcohols don't oxidize easily. So, I say they don't oxidize easily for the purposes of A1, your first year, they don't oxidize at all. There are some reagents that can oxidize them, but they're not any of the ones that are listed. So, that's why it's going to be answer D, none of them. Then it asks for the COH bond angle in the molecule below. Now, if you look at the molecule, you'll see it's an alcohol. If you look more closely, you'll see it's, I think it's butanol. But what they want is the COH bond angle. So if we were to draw it out in a slightly more displayed form, we have a CH3 on the end. We'd have an H coming off the second carbon, 2 H's on the third carbon, and 3 H's on the fourth. Now if we also draw out the OH group, the hydroxyl group, if you remember, oxygen has 2 lone pairs. And therefore that means it adopts a non-linear shape. It's analogous to water, isn't it? So it's going to be 104.5. So the recall required here is shapes of molecules, but there's also a bit of application. And that's transferring the shape of water that you would have learned in your recall work and your flashcard work with shapes of molecules across to the carbon-oxygen-hydrogen bond. So, question number 5 says, which of the following represents a redox reaction, e.g. oxidation and reduction? And the clue to look for here is that redox reactions often include uncombined elements. So if we look closely, we can see that the first one has uncombined hydrogen on one side and uncombined calcium on the other. So the calcium has become combined, and the hydrogen has become uncombined. Whoops, sorry. That must mean a transfer of electrons between them. So therefore, what we're looking at is answer A. So let's now go on to the next question. It says, suggest an appropriate notation to represent the enthalpy change of this reaction. Now, this is one where you've got to look carefully at the options. You've got a combustion. Now, it can't be a combustion because it's not calcium reacting with oxygen. So that's this one out. It's not a neutralization, even though there's an acid present, because it would have to be a base reacting with an acid. And you haven't got a base reacting with an acid, you've got a metal reacting with an acid, so it's not delta neut H either. Now, for it to be delta FH for calcium sulfate, you'd have to have the original uncombined constituent elements in their correct molar ratios and in their standard states. The definition for delta FH is not actually being obeyed here, because although you have calcium, you don't have hydrogen on its own, you don't have sulfur on its own, you don't have oxygen on its own. So it's not that one either. So it's the default one, isn't it? Delta RH, the more general description of an enthalpy change. So it's going to be answer A. Now this was definitely recall. And what it required you to be able to do is to eliminate B, C and D by knowing the definitions of delta FH, delta CH and delta neut H. If you struggle with this one, it's simply that, I'm sorry if you haven't gone away and revised those effectively enough, you've got to now go back and memorize those off by heart so that you'll be able to spot that straight away. So the kind of things you need to be able to do across all of these multiple choice questions is recall. They're a very strong test of your recall. Occasionally they'll do application as well, but if the recall isn't there, sorry, you're not going to do very well. And it's very interesting from a teacher's perspective to mark a paper that has a section of multiple choice in it. You can already tell by the time you've marked the multiple choice section, only 6 questions at the beginning, how well someone's going to do. You can almost predict it, because if their recall is strong, they'll make it all the way through the multiple choice section, getting all the questions right. If their recall is poor or hasn't been worked on, they'll wobble on a couple of them, and that will generally pan out in the percentage that they'll get at the end. Not always, but just a little bit of advice from the other side. Make sure your recall is good so you can do multiple choice questions. Then the longer style extended response questions will take care of themselves because you have the recall at your fingertips. So let's now have a look at some of those styles of extended response questions. So the first question is talking about tungsten. Tungsten isn't one you're expected to know about, so this is not recalling about tungsten, but it is recalling about isotopes. So at this point I'm going to switch to putting my recall application advice in blue and my answers in red. So there's 2 things I need to say about this definition. First of all, that there are 2 parts to it, and secondly that you have to get both of them to get 1 mark. This is reflective of the type of more strict marking that the newer specifications will require. Okay, so the first thing to say is it's atoms of an element. You have to say it's got different numbers of neutrons and different masses. All of that is required to get your mark. It's a simple case of making sure you memorize it. Don't try and be creative about it. Don't try and say it in a different way. Don't try and be overly clever, because that's not going to get you anywhere with an examiner. All an examiner is interested in is, do you know the definition in that particular type of question? If they wanted you to explain what you thought it meant in terms of being creative, in terms of going further, in terms of applying it to another element, for example, they'd ask you. The question says, explain what is meant by isotopes. That wording says to me they want the definition, particularly as it's 1 mark. So let's now move the question down a bit, and it says the mass number of 1 isotope of tungsten is 184. So at this point you need to have your periodic table in front of you so you can get the number of protons in that isotope. Because remember, the number of protons and the number of electrons will stay the same. It's the number of neutrons that are different. So looking at tungsten in the periodic table, you can see that it's got 74 protons. That requires you to recall that the number of protons equals the number of electrons in a neutral atom. Now, if you look at the mass number, which means the protons and neutrons, it's 184. So therefore, you take away 74 from that to get the number of neutrons, which gives us 110. Now the next question says, what is used as the standard measurement of relative isotopic mass? And at this point you need to remember that carbon-12 is the standard isotope that's used to define things like relative atomic mass, relative isotopic mass. So therefore that's what we're after. Okay, moving the page down a little bit. It says, in the manufacture of tungsten metal, an oxide of tungsten is reacted with hydrogen gas. So what I suggest, because obviously the question itself goes on to the next page, is you jot this down on a piece of paper. So if you pause the video clip and just write that equation down, then I'll go to the next page where it will require you to know it, or at least to be able to refer to it. So I've written it down at the top of the page, and it says, using oxidation numbers, show what's been oxidized and what has been reduced in this reaction. That's for 2 marks. So what I'd suggest the first thing to do is to assign oxidation numbers to all of the species. So it requires you to be able to recall the oxidation number rules, such as oxygen always being, or mostly being, -2. Hydrogen generally being +1 in compounds, etc., etc. So I've put in the oxidation numbers, being careful to assign them to individual atoms. For instance, WO3 doesn't have oxygen being minus 6 because there's 3 of them. Each oxygen atom is minus 2. And it goes so far as to say that's something you have to remember when you're applying the oxidation number rules. So starting out with tungsten, let's highlight it and follow it from one side to the other. So that transfer of oxidation number, that change in oxidation number, is a reduction because it's dropped in oxidation number. It's gone from plus 6 to 0. So now if we apply the same idea to hydrogen, I'm going to highlight this in a slightly different shade. And you can see that this goes from 0 in hydrogen gas to plus 1 in water. So this obviously represents an increase in the oxidation number, so that means hydrogen is oxidized. So next up is a calculation question, because you can tell there's some data that's being given to you. So let's move the page up and just highlight the data. Just realizing to move the page down a little bit because we need to be able to see the equation. Okay, so we've got 11.59 grams of WO3, and it asks you to calculate the volume of hydrogen gas in decimeters cubed required to completely react with this mass of WO3 at room temperature and pressure. Now, I would suggest at this point using the data moles equation moles answer technique. So I'll take you through that. So if we divide mass over MR, we have 11.59 over 2 through 1.8, giving us 0.05 moles of tungsten oxide. So looking at the mole ratio of tungsten oxide to hydrogen, it's 1 to 3 from the equation. So therefore the moles of hydrogen is going to be 3 times 0.05 equals 0.15. Now we can get the answer. Because it's a gas, you can use V equals 24N. So that gives us 24 times 0.15. So the recall required is moles equals mass over MR and V equals 24N. So those will come from boot camping and recall practice. And for practicing past paper questions, we'll give you the application skill to know which to use and when. Let's move the page down to look at part C. So you can see quite clearly this is an ionization energy question, and it's asking you to compare two elements together. Xenon has a lower first ionization energy than neon. So, what do you have to do? You need to be able to make 3 distinct points on comparison of one element versus another. So we need to discuss atomic radius, shielding, and nuclear attraction. Oh, just had to quickly correct that. Xenon has a bigger atomic radius than neon. Xenon has more shielding than neon. And finally, the outermost electrons in neon experience lower nuclear attraction than those in... Outermost electrons in xenon experience lower nuclear attraction than those in neon. So let's pause for a second and have a look at things you shouldn't write, things that will not get you marks. So the first thing not to do is to say what the question already tells you. For instance, you shouldn't say that xenon has a lower first ionization energy than neon. Why would they give you marks for that if they've already told you? The second thing not to do is contradict yourself. This requires you to read your answer back to yourself and check that you haven't done this. I know that in an examination setting it's sometimes easy not to realise this is what you're doing. This is where you need to pause every 15 minutes or so, make sure you're A, on time, and B, that you're actually reading your answers back to yourself so that you can spot mistakes as you go. And don't say the same thing twice, but in different words just to fill space. The examiner will spot that, and you won't get an extra mark at all for saying it twice. In fact, what they'll do is they'll find the one that's more incorrect and mark that, because then it shows that you're unsure of what you're writing. So once you've made a point, leave it, go on to another point. So how do we make sure that we organise our thinking as we go? Use bullet points. I guarantee you, it will help you organise your thinking. You won't end up making those mistakes. Right, so this next question is about our old friend enthalpy. It gives you a little bit of information, background information about phosphoric acid. You don't really need to know that background information, it just introduces the idea. But it does give you delta FH data. So delta FH data is quite important in the sense that you need to know what to do with your delta FH data and how to use it. So there's a bit of recall and application going on in this particular question, in part A at least. If you didn't do very well in this question when you tried the homework, you might want to pause the clip and go and get your flashcard for delta FH, or the part of your notes in your independent study that have delta FH explained. So we're talking about the first reaction. It says delta RH1 represents the enthalpy change of formation of P4O10. So if we look at what's happening, we've got the P4, we've got 5O2. They're both uncombined elements, aren't they? They're both in their standard states, and they're creating our product in its standard state. So we need to say something about that. So therefore 1 mole of P4O10 is being formed from its constituent elements. That would get you one of the 2 marks. The other is to make something of the fact that they're all in their standard states. So that would get you your 2nd mark. Okay, so the next question is about delta RH2, the second reaction. I'm going to find a slightly different shade when I'm highlighting this, just so we don't get confused. And move the page down because we need to have a little bit of room. I'm going to leave the equation up at the top though, so we can see what we're doing. So I would suggest always doing a Hesse cycle. So now we've got our reaction. I've colour-coded it so you can see which one in the question I'm referring to. It's the pink one, not the red one. So we have enthalpy changes of formation. It's very important that we highlight that. So that we know what we're doing with the data we've been given. So when you have enthalpy changes of formation, you need to put the elements in their standard states in the correct mole ratios beneath your main equation. I usually get my students to put them into a little box like that. Then you know where they are, and you can point away from that box at the various compounds. So you have everything in that box can come together to make 4 moles of H3PO4. Or everything in that box can come together to make 1 mole of P4O10 and 6 moles of water. So now what you do is you have your independent route. So we're going to follow that independent route. So our expression is minus delta FH of P4O10 because the independent route, the arrow is going in the opposite direction to the pink arrow that shows the formation of P4O10. So that means it's going to be positive 2984. Next up comes 6 H2Os. Now, to form 6 H2Os, you have to go from the elements at the bottom to the 6 H2O at the top. Again, the independent route is travelling in the opposite direction. So that's going to be 6 times 2H6. Notice I'm swapping the sign to positive because minus 2H6 makes plus 2H6. And finally, I'm going in the same direction on the right hand side as the formation of 4H3PO4. So that is 1267 times 4. So grab your calculator and put those in, and hopefully we'll end up with the right answer together. I got minus 368. Hopefully you did as well. If you didn't, go back and work your way through it again. Rewind the clip, have a listen, and go through it one more time. Because this question, this particular part, is a little bit more challenging. But understanding and being able to apply Hesse's law will basically open every single enthalpy question you will see at A level to being able to be solved. So if you need to go and do a little bit of recall work on Hesse cycles, it's well worth going back and doing that after this clip. So let's now go down to the final part of the question. Bottom. It says, write the overall equation for the manufacture of H3PO4 from P4, and then use the equation to explain why the process has a 100% atom economy. So that should be fairly straightforward. So what you've got to do is look really carefully at the two equations that you were given at the beginning of the question. So you want to make H3PO4. In the first step, you make P4O10, and in the second step, you use up that P4O10 by reacting it with 6 waters. So what I mean is, in step 1, you produce P4O10, and in step 2, you use it up. So you can actually cancel it out. This now leaves you all of this as your main reactants, and only this as your final product. So that's what needs to go into your equation. And because there's only one product, or only the desired product is made, therefore it's automatically 100% atom economy. So let's now go on to the next part of the paper. So in question number 3, it's obviously about spectroscopy. Now, the first part is really easy, A part I, because all it requires you to do is to use your data sheet. So at this point you may wish to go and grab your data sheet and have it with you. Because if you don't have it with you, it may or may not make sense what I'm about to say. You'll need to have the data sheet with you so you can see what I'm referring to and show you how easy it is to get the mark here. Now be very careful to actually use the data that's on your data sheet, not anything that's slightly different. They expect you to be 100% accurate when you're doing that because they give you the information you need to use. So please don't try and put a value down that's slightly outside the range they give you. It must be within the range they provide. So any 2 out of those 3 ranges will do. It doesn't ask you to say what specific bonds they relate to, it just asks you to state or suggest 2 possible characteristic infrared absorptions that could be used. Now the next part requires recall of oxidation of alcohols, specifically the colour change that you get from the reduction of the dichromate. So the dichromate acidified is your oxidizing agent, so it itself is reduced. Okay, so the next part of the question asks you for an equation. There's a bit of recall required here as well. And that is the correct or appropriate balanced equation for alcohol and oxygen from an oxidizing agent. So you have to think about what kind of alcohol you've got and what it's going to oxidize to, if at all. So ethanol is a primary alcohol. So you could either put down its partial oxidation to an aldehyde, or you could put down its full oxidation to a carboxylic acid, which I'm about to show you. The important thing is to get the right number of O's in there, O's in square brackets, and the fact that you've got an H2O. This is where people come unstuck because they haven't done the recall I've just suggested. They've kind of got it and think they can sort of wing it on the day. The number of times you see people, even in A2, getting this wrong is actually quite interesting. So make sure that when you're going through this, and if at any point you struggled with this particular part of the question, that you go back and do the recall. Make those flashcards and learn them. So the next part of the question has an infrared spectrum, and as you can see from the screen, we're almost at the bottom of that particular page. So I suspect what's going to happen is the question is going to ask us about that, and I'm going to have to put it on the next page, so give me 2 seconds to sort that out. So hopefully you can see that you've got the beginning of the question from the previous screen, the top right hand corner of the page, and you've got the mass spectrum. Because you've got to use both to try and work out the reason why compound A is a hydrocarbon. So the first thing to do is to look at the infrared spectrum, because that tells you the bonds present. So I can see from my data sheet that that peak at just before 3000 centimeters to the -1 refers to CH. So the first point to make is that there's a carbon-hydrogen bond absorption around 2850 to 3100 centimeters to the -1. And now the second mark is for saying there's no other major absorptions. And the reason that's important is because the presence of other significant absorptions, large peaks, would indicate the presence of other functional groups or bonds, which would mean it's not just a hydrocarbon, now it might be a different kind of molecule, like an alcohol or something like that. So quite often it's important to remember that infrared spectroscopy tells you something because of what's not there, as well as because of what is there. Now it asks us to look at the mass spectrum. It says, how does the mass spectrum confirm that compound A has a molecular formula of C4H10? Now that tells us that the M plus peak, a bit of recall here, reminding yourself that the M plus peak, the MZ value of that peak equals the MR of the molecule. So looking at that value, is 58. So that value obviously matches the MR of C4H10, which is 58 grams per mole to the -1. So now it asks us to draw the structural isomers of C4H10. So at this point, it's worth pointing out that provided your structure is unambiguous, it doesn't say specifically what type of formula, you can do it any way you wish. So I'm going to do it in a partially displayed form. So those are your two possible answers, which you must type both of them in order to get the mark. Now the next one, it says fragment ions, and the most common mistake here is to forget that we're talking about ions and just put down the structure of the ion but without giving its positive charge. So with that in mind, we can now start deducing what might be 15, what might be 29. So you start with carbon, because it's the bigger of the two atoms, that's what I'd suggest. So you do carbon and hydrogen first of all. Okay, now that obviously isn't an ion, that's a very strange looking species, but if you take carbon as being 12, you then need to add 3 to 12 to make 15, so that could be your candidate. For 29, how many carbons can you fit into 29? 2. That brings you to 24, so 5 more hydrogens. 3 carbons is 36. How many hydrogens can you add onto that to make 43? 7. So let's go on to the next part of the question. Now, again, it requires you to have a look at the spectrum, doesn't it? It says, use your answer to part IV to identify which of the isomers in part III is the compound A. Then explain your reasoning. Okay, so we also need the spectrum itself, don't we? So it's essentially getting you to think about the spectrum. What are the 3 fragments from part IV, and which one out of the 2 isotopes from part III is compound A? So what you've got to do is think to yourself, what might create a C2H5 fragment? It's actually the top answer, because that could break down the middle, as I've indicated, to make 2 lots of C2H5+. If you think about where the bottom one would break, it would produce CH3+, if it broke there. And it would also produce, if it broke there, the other remaining part of the molecule, which I'm just going to highlight for you. That would be quite a large fragment. That's not C2H5. So therefore, our fragment, sorry, beg your pardon, our isomer that we're after is this one. So the way you'd word it is you'd say CH3, CH2, CH2, CH3, because this isomer could easily fragment to produce C2H5+. That was actually quite a lot of work to do for 1 mark, but then that would be the mark that would discriminate between your A and your A star. There will be a question of that magnitude of challenge at some point in every exam that you take, and it may not necessarily be a lot of marks available. You'll have to think harder for the same mark as maybe an easier one earlier on, like a multiple choice question, for example. Right, so let's have a look at the remainder of the question. So looking at the question, there's actually no more left on that particular one, so let's move it down to question number 4. Okay, so this is obviously a mechanism style question. It looks to me like it's the electrophilic addition, and that is just pure recall again. Now they want methyl propene with bromine, so let's give them it. So you start by drawing your bromine electrophile. It's been polarized because obviously the electron density has been moved away from one bromine towards the other by the repulsion effect of the electron-dense carbon-carbon double bond. This now means that electrons are attracted from the carbon-carbon double bond. I need to make sure I'm actually touching the bond, like that, and touching the bromine atom. It has to be the delta plus atom. Now I break the bond between the bromine atoms heterolytically. Again, my curly arrow has to start at the bond. There we go. It's a little bit tricky on the iPad sometimes. So that's our first stage. We get 2 marks for that bit. Now what we have to do is draw the intermediate. Now we've got to be a little bit careful here because it's an asymmetric alkene, isn't it? So you need to recall structures here of the correct carbocation. And this states that the atom, the incoming bromine, the bromine that adds, first of all, will add to the carbon that has the most number of hydrogens. So it's the carbon on the left-hand side. So the bromine adds there, because that then allows us to create the more stable carbocation, the tertiary structure, which is that one there. So you give that carbon a positive charge, and don't forget you also have a bromide ion. You don't have to have a lone pair on it, but I like to put a lone pair on it, because then it allows me to say exactly where the electrons begin, and they need to point directly at the positively charged atom, positively charged carbon atom on that carbocation. So that's me done for that. It doesn't say to draw the product, it just says to draw the mechanism. Now, the next part of the question, it shifts, doesn't it, over to polymers. It says fluoroalkenes are used to make polymers, for example, PVF, CH2CHFN. Now what I do initially is I draw that out, even though the question doesn't ask me to. I draw it out as a technique tip here, so I know what I'm dealing with. So what it wants is 2 repeat units. Really important here. There's not 1 repeat unit, it's 2 repeat units. So we draw it like that, what 2 of that alkene joined together would look like. Now you must leave the trailing bonds on either side. By trailing bonds, I mean these 2. They must be included. So now what you can do, if you wish, is to put the brackets in. And you can put in the value of n. You don't have to do an algebraic version of n because it's 2 repeating units, because you're not specifying how many of those original monomers, the the original monomer being this, of course. You're not specifying how many of them are present, so you don't want to justify whether it's n or n over 2 or n over 4 or whatever. If you do put the square brackets in, and notice I said if, you don't have to, but if you do put them in, they should overlap the trading bonds like that. Okay, let's move on to the next part of the question. It asks you to draw the structure of the monomer of PVF. Well, it's interesting, we did that before, didn't we? Just to clarify in our minds what we were going to do. So as you probably recall, it looks something like that. Now the next question looks suspiciously like calorimetry, doesn't it? You can see from the diagram it's something that you'll have done in the lab. So let's move the page down a bit so we can get stuck in there. It's 4 marks, quite nicely, it can fit into this screen. So it says, suggest with a reason one procedural error, one mistake, from the picture above. Now if you look at the diagram, the thermometer appears to be suspended in midair. If the thermometer was touching the calorimeter in the container, it wouldn't necessarily be measuring the heat of the water, it would be measuring the heat of the container itself. And finally, the beaker itself. Mostly beakers are made of glass or plastic. Not ideal, the plastic would melt or the glass wouldn't conduct the heat from the flame into the water. So the beaker should be made of metal. So the next part says the student found the value for delta CH that they calculated was significantly less than the value they looked up in a database. And the reason for this would be heat loss. And that would cause a reduction in the delta T value in Q equals mc delta T. And finally it says the thermometer has a plus or minus 0.5 degrees C uncertainty range. So the student measured a 34 degrees C increase in temperature, and they want you to calculate the percentage uncertainty in this measurement. So what you need to remember to do here is to multiply your uncertainty by 2. Because the increase in temperature requires a starting temperature and a final temperature, so there's 2 readings taken. And hopefully you can just about make out what I've written in the corner there. Uncertainty is multiplied by 2 if the measurement is being made by difference. So if 2 readings taken, then you will multiply by 2, like that. So hopefully this has been a fairly useful clip. I'm hoping that obviously you've tried the homework first before watching this clip. The idea is to illustrate to you some techniques you might want to apply, to illustrate the importance of recall and how recall can actually feed into the accuracy of your exam questions, your answers rather. And in addition, the idea that to address the recall, you have to get the boot camping done. You have to make sure that what you're doing is look, cover, write, check, repeat. Until that process happens, and your recall is improved, you're going to find it difficult to apply that knowledge to the kind of questions that are in this homework. So once again, thanks for your time, appreciate you listening, and see you soon.